So at this stage in the process, you found your data set, you've collected and cleaned your data, and you're ready to start analyzing it and drawing some conclusions. First of all, congratulations on making it through the first stage of a data analysis project, which, while one of the more tedious steps, is also one of the most important. As the old statistical saying goes, garbage in, garbage out. But now that we've carefully selected our data and know that we aren't working with garbage, we can really get to the good stuff and start analyzing our data and drawing some conclusions. Today, in order to get you ready for the next step of your project, we're going to go over some basic statistics that will come in handy when you analyze your data. And to do that, we need to talk about three things: fire trucks, ice cream, and Nicolas Cage. Let's get started. Like we talked about in the last video, one of the most common data jam projects is trying to find a correlation between two or more variables. For this reason, today I'm going to talk about the three biggest mistakes that are often made when using correlation, or as I like to call them, the three correlation irritations. And believe it or not, these things all do end up relating back to fire trucks, ice cream, and Nicolas Cage. Now, you may have heard the old statistical saying that correlation does not imply causation. This is huge with the data jam because oftentimes teams will analyze their data and find that a correlation does exist between the variables that they're examining. If you find this out, that's great. But just because you know two variables are correlated, you cannot necessarily conclude from that one of these variables is causing the other. Now, you've probably heard this before, but today we're going to dive into exactly why this is the case and what happens when you ignore one of the cardinal rules of statistics. The first correlation irritation relates to fire trucks and is known as a reverse correlation. Reverse correlation is the first reason you can't assume causation from correlation. And to explain it, let's look at an example. Imagine you were trying to investigate the correlation between the damage caused by a fire, which you measure in monetary value, and the number of fire trucks that were at the fire. When you do this, you will see a correlation between the amount of damage and the number of fire trucks at the scene. It makes sense because greater damages require a greater number of fire trucks to arrive and help put out the fire. You might then jump to the conclusion that the damage is causing more fire trucks to show up. However, if you can conclude causation one way, it has to work the other way too, and this is where things get tricky. If you were to reverse your analysis, the number of fire trucks arriving at a scene are also correlated with higher damages. Therefore, inferring causation this way would lead to the false conclusion that the fire trucks arriving are causing more damage. Imagine if a local fire chief jumped to this conclusion and then sent less fire trucks to a fire because he thought they were causing damage. The results would be catastrophic. Now, in this case, it's pretty apparent that fire trucks aren't causing the fires, but in other examples, it's not always so clear. This is why reverse correlation can be so dangerous and is the first reason that correlation does not imply causation. If you're confused by this, you're not alone. And believe it or not, a prominent statistician actually made the exact mistake of reverse correlation when investigating a correlation between smoking and lung cancer. Because these two factors are so closely correlated, he ended up reversing the correlation and then concluded that lung cancer was causing people to smoke instead of the other way around. Unsurprisingly, this statistician was a known smoker himself. In these examples, we can clearly see that if you determine causation from correlation, it can go both ways with a reverse correlation, and this is one of the main reasons we can't do it. Second correlation irritation is a big one, and this is confounding variables. To illustrate confounding variables, let's talk about ice cream sales. If you were to examine a correlation between ice cream sales and murder rates, you're actually going to find a strong positive correlation. Does this mean that ice cream is driving people to murder? Well, what is actually going on here is that murder rates increase with another variable, temperature, which in this case is a confounding variable. In the summer, as the weather gets hotter, it's well documented that more and more people are outside and more irritable, and murder rates will increase. However, ice cream sales also increase in the summer, so temperature acts as a middleman between the two and causes them to increase at the same time. This is another reason you can't imply causation from correlation. You never know what intermediate variables are actually causing the changes, so when you conclude that correlation implies causation, you don't know what you're actually concluding. The third correlation irritation is called a spurious correlation, and this finally brings us to Nicolas Cage. Pictured here is one of the more interesting graphs you'll see, which charts the number of people who drowned by falling into a pool against the number of films that Nicolas Cage appeared in that year. And if you look at the graph, they're actually very closely correlated. So does this mean that Nicolas Cage's acting was so poor it physically knocked people out of their chairs and into pools where they drowned? Well, if you're implying causation from correlation, it might, but this is actually an example of a spurious correlation because it's a pure result of random coincidence. Linked below is a website that compiles more crazy correlations like this one, such as the correlation between per capita consumption of mozzarella cheese and civil engineering doctorates, or people who drowned falling out of a fishing boat and the marriage rate in Kentucky. These spurious correlations are random, and one factor is definitely not causing another. This is just a final reminder of why we can't infer causation from correlation. Now we've gone over our three correlation irritations of reverse correlation, confounding variables, and spurious correlations. We know a little bit more about why correlation doesn't imply causation. Naturally, this raises the question, how the heck are you supposed to prove a causation? And the answer to this is that the best way to do it is with a controlled experiment, which requires another set of rules and procedures to follow, which could be the topic of a whole video series in and of itself. The only other time you're allowed to do it is in some rare cases if such a strong correlation is proved in multiple different ways. Only then can a correlation be cautiously inferred. This is what happened with early studies on smoking and lung cancer, because it wasn't ethical to run experiments that forced people to smoke. But unless that's the case, now we know if you detect a correlation, you've got to be cautious about implying a causation. Thank you so much for watching today. I hope you learned something about correlation, causation, and more of the why behind why they work. Stay tuned for next week as I apply these rules to the analysis of my project and call in the help of another Data Jam mentor. Thanks so much for watching. I'll see you in the next one.